Okay, here we are. I think this is the final frontier, the last video. We have a 22 kilogram block being moved to the right at constant velocity. As soon as you see that, you are thinking total force is 0, balance of the forces balance, right? Constant velocity means that the acceleration, the change in velocity is 0, because there's no change, so the acceleration is 0. Therefore, the net force, which is m times a big fat 0, is going to be 0. Forces balance. Just like we wrote. A, good. Okay, the normal force, it's being moved to the right at constant velocity along a horizontal surface. That's important too. It's not a ramp problem. So there's our block, constant velocity. The normal force is 140 newtons. The coefficient of kinetic friction between the block and the floor, mu, mu k is 0.55. Right? Kinetic friction. It's moving, so there's friction pulling the opposite way. It's moving to the right, so kinetic friction pulls left. Draw a free body diagram. We're almost finished. Find the magnitude and direction of the applied force. Right? So what pulls down? Gravity. And gravity is going to be stronger than that. mg, m is 22 times 9.8 gives us 215.6. So look at this. Right now, there is nothing balancing Fk. So we have to draw a right force balancing Fk. And there's nothing, let's see, Fn is 140, but mg is a lot bigger. So right now, there's a larger down force. So we need some up force in order to make the up forces this plus this value, whatever it is. That's what has to equal mg. So there has to be another up force in order for the ups to balance the downs. So we look at that drawing, we see, hey, check it out. The applied force has got to be up at this angle. So we're going to find the value of Fa as well as theta. I'm going to call the up, I'm going to call that Fa comma x. Nope, that's not right. Fa comma y, and this one down here is Fa comma x. Right, like that. Okay, and of course I can kind of squiggle out of Fa if I care to, because I've shown its components. So left balances right, balancing. What pulls left? What pulls left? All I see in my picture, I look at it, I see one left force, Fk. So I'm going to erase F left, replace it with Fk. What pulls right? I only see one right force in my picture, Fa comma x. Fax. You all probably don't know what a fax is. You're like, what's a fax? I only know email. Okay. Then we also can balance up and down. Right? So what pulls up? Well, I look at my picture, I see this one, 140, and that one, Fay. So let me put in 140 plus Fa comma y. What pulls down? Just mg. Just the 215.6 newtons. And I'm going to take this out. Right? So check it out. If we can find Fax and Fay, then we can easily find the applied force, our unknown, because it's just equal to, well, it's the hypotenuse, right? It has components. It's the hypotenuse. Pythagorean theorem gives us the hypotenuse. So how are we going to find f(ax)? Oh yeah, fk is mu times fn. Like that. Mu is 0.55. The normal force is 1 for zip. And that's how we find f(ax). So 0.55 times 140. Oh, that's not what I wanted to calculate. That gives us 77. So I'm just going to erase because I have actually gone as far as the smartboard can go. I cannot go down. I can't extend any further. It does not work. I reached the end of the smartboard page. I feel pretty accomplished. Okay, 77 newtons. Fay we easily solve for. You subtract 140 from both sides. Minus 140. And that's a 75.6. So you use this equation. You find Fa. Easy. I don't need to do it, but I will. And so it's the square root of 77 squared. Right? Fax is 77, so I put 77 right there. And then here I put 75.6. And I get, when I square root it all, I get Fax equals 107.9, or I'll just call it 108. Now theta, we see theta is up from horizontal right. You see that? It's pointing up. The way you find theta is it's the inverse tangent of opposite over adjacent, right? So what is opposite theta? Fay. That's the top right here. What is adjacent theta? Fax. So theta is inverse tan of 75.6 Fay over 77 Fax. Inverse tan, where are you? 75.6, where have you been my whole life? And theta comes to, well, I'm out of room because I can't extend down any further. So let me just erase my work. Something you should never do. 44 degrees up from horizontal right. Boom. Next one. Ramp time. Booyah. Where'd my ramp problem go? Come on, show up. Let's see. This is funny. This happens every now and then. There it is. Okay. A 3.2 kilogram block, that sure is the mass, isn't it? Kilograms mass, is sliding down a ramp inclined at 18 degrees. We want the block always to be going rightward in our picture. So I'm going to draw the block the ramp this way. This is 18 degreesios. That's not a word. The coefficient of friction, and it's sliding, so this must be the coefficient of kinetic friction, is 0.26. But I'll make sure I improve the language of the problem to state specifically kinetic friction. That's 0.26. Find the block's acceleration down the ramp. Okay. So on the block we have the normal force pushing up, gravity pulling down. Whoa. Normal force pushes up, gravity pushes down. Let's see. And I'm going to move all of this down so I have more room to work. And let me make my normal force. My normal farce. The farce is a little bigger. And then kinetic friction opposes the motion down the ramp, so it pulls back up the ramp. This is mg. Right. mg has a tilted y component perpendicular to the ramp and a tilted x component parallel to the ramp. Have I done a good job? Did I draw my x component parallel? It's pretty parallel. Maybe I should angle it a little more. That's a little better. A little bit better. And is this one really perpendicular? It's close enough. close enough to perpendicular. So this should be a right angle, right? Okay then, if 18 is that angle, then 18 is also this angle. There's a nice little proof, similar triangles gets us there. That makes this mg cos 18. And this is mg sine 18. We have acceleration down the ramp. Down the ramp only. So that tilted y component equals that tilted y component. They balance. If they didn't balance, the block would either be accelerating off the ramp or into the ramp. Neither of those is happening. We accelerate down. Okay then, that means Fn balances mg cosine theta 18. Now here's the thing, right? We just said the total y force is 0 because there's no acceleration off the ramp. So the total x force is where we have acceleration. We can apply Newton's second law only to the x direction, and we get that when we do so. So if we want to find the acceleration down the ramp, we need to know the mass, and we do. But we also need to know all of the x direction forces. That means we have to be able to find first Fk, and we can find that. We know mass, we know g, we know 18. So if we find Fk, then we can plug in all of our x forces, plug in the mass, and solve for the acceleration a sub x. That's our roadmap, okay? We want to find all of the x forces. Find them. Where are they? It's like a treasure hunt, right? Okay, I'm going to go ahead and write in what are the x forces. There's Fk pulling to the left there. And then the only other x force that I have in my picture is that one right there, which is mg sine 18. So how do I find Fk? Well, Fk is mu times the normal force. The normal force is replaceable with mg cos 18. So let's replace it. If you plug in the values, mu, right, is 0.26, 0.26, and show this work, write it out in your work. The mass is 3.2, g is 9.8, cosine 18, so many things in this calculation. Make sure you're in degrees. You get 7.75. Right. Now we can easily find the acceleration down the ramp. We just found Fk, 7.75, plus, what's the mass? 3.2 times 9.8, sine our 18, 3.2 again. Oh, don't put the weight right there, just put the mass. Right? And you solve for the acceleration. Evaluate, that's a fancy word for calculate. Evaluate the left side and divide it by 3.2. So when I evaluate the left side, I get 1.9 newtons. I sure hope I did this right. It's not looking super correct right now. 3.2, I guess it is. Suppose it is. And when I divide both sides by 3.2, I get 0.61. Like that. There is the acceleration down the ramp. You don't really need to write down the ramp because the problem said find the acceleration down the ramp. That was given. Okay. That's all we have time for right now in this video.